Welcome to the second part of Chemical Reactions Notes. This is 5.3 Metal Reactivity Series and 5.4 Balancing Chemical Equations. You must watch this video slowly and carefully while taking notes because you are going to use balancing chemical equations principles for the rest of chemistry. So what is the metal reactivity series? It's a set of metals from the periodic table arranged based on their rank on reactivity. So reactivity of metals is their ability to donate valence electrons and form cations. You can review these notes in 3.10 periodic table notes video. So we encountered this diagram in that video showing metallic nature, how it increases as you go across the periodic table. Essentially, when you go from left to right, metallic nature or metal reactivity increases, and also when you go from top to bottom. So the most reactive metals are on this side of the periodic table. So sodium is more reactive than lithium in the same group, and sodium is less reactive than potassium, and potassium is more reactive than calcium, and sodium is more reactive than magnesium. That's how you need to think about it. So I have color coded the metals based on reactivity. As you become more blue going up, the reactivity increases, and I have placed hydrogen, which is a non-metal, for comparison, because in some reactions you will have to figure out if a metal can displace hydrogen or not. So any of the metals below hydrogen on this figure cannot displace hydrogen, and they are unreactive. The most reactive ones are over here. These all react with water and form hydrogen gas and a base. These guys react with acids and form salts. Let's look at the rest of the notes. So you must keep in mind you're going to use this metal reactivity series only when you are doing single displacement reactions. That is one element, that is a metal, trying to displace or kick away a metal that's in a ionic compound. So here's an example: copper chloride and sodium. Can sodium kick copper out and hang out with chlorine? So to do this, you need to know where they are. Sodium is above copper, so sodium can indeed kick copper out and displace it. So this is called a single displacement reaction, and you have sodium chloride and copper being precipitated. This is a reaction where you will see a powdery copper forming at the bottom of the tube, which is an evidence of a chemical reaction. And then what about this one? This is a double displacement reaction. You have two compounds. They are both ionic compounds. Here you don't have to worry about the metal reactivity series because one metal is always stronger than the other and both compounds get displaced. You swap the cations and the anions. So you will make calcium nitrate and barium bromide like shown over here. You need to know how to write polyatomic ion compounds as we did in 4.2 lesson. So remember, weaker metals cannot displace stronger metals. So if such a situation happens, you will not see any reaction. I reverse this reaction. Sodium chloride and copper. Sodium is way above copper, as you can see. And when sodium is married to someone, copper cannot kick it out and you will not get a reaction. Again, these metal reactivity series only matters when you are talking about single displacement reactions, when you have a single element trying to kick a metal away from its compound partner. Again, you have to review the polyatomic ions over here. I put it up here for you to remember. And Now let's try some problems. Predict the products of these chemical equations. As mentioned above, here are the things you need to know in green. Please watch these videos again. So lead chloride and zinc, will they make a product? So here is lead and zinc. Zinc is the single guy. He has to be above the guy he's going to kick away, and indeed they are. So zinc chloride and lead precipitate is going to be made. Lead is going to become a solid and end at the bottom of the tube. Magnesium and lithium chloride, you do not have to worry about this because this is a two ionic compounds. You don't have to worry about the metal reactivity series. You will have pluses and minuses swapping. You will have magnesium chloride and lithium bromide being formed. And again, this is a similar problem. You're going to have calcium nitrate and aluminum hydroxide being formed. You need to know their chemical formulas from crisscross method. Since calcium makes 2 plus ions and OH is a minus 1, it's going to have CaOH twice. And when calcium marries nitrate, nitrate is a minus 1 and calcium is a plus 2, so it's going to be CaNO3 twice. Aluminum is a plus 3, and when aluminum marries hydroxide, it's going to be AlOH 3 times. Because OH is minus 1, aluminum doesn't get an coefficient here. Can you write this equation? Zinc plus aluminum nitrate. Since you have a single element, you need to be able to look at zinc and aluminum. There you go. So they are going to make zinc and aluminum nitrate, and will that react? Zinc is trying to kick aluminum away. Zinc is below aluminum, so there will be no reaction. Practice these kind of reactions on your own and until you get better at them. So let's look at the steps to balancing equations. Step 1 is to count the atoms of each element on each side of the equation. We practice that. And the second one, change in only coefficients on each side of the equation, not the subscript that comes after the element. We practiced doing this in the previous lesson. The black ones are the new ones. When dealing with a specific polyatomic ion that occurs on both sides, treat it as one element. If the two sides have different numbers of the same element, make the numbers equal to the least common multiple, or LCM. You studied LCM probably in grade 6, I think, for math. Quick review. So say you have 2 of something on the reactant side and 3 of that stuff on the product side. So you have to find a number that is that has this 2, that is a multiple of 2 and 3, the smallest one, that is going to be 6. So you're going to make both sides equal to 6. You will multiply the left side by 3 and the right side by 2. And number 5, balance oxygen atoms last when you have reactants with multiple oxygens. The balanced mole ratio should be the simplest whole number ratio of coefficients. For example, after you balance everything, you should not have a ratio like 3:6:6:6:3. So 2 of these are reactants and the other 2 are products, because you can divide this further and by 3, and then you get 1:2:2:2:1. Okay, so the first practice problem is very simple. You have carbon combining with oxygen to form carbon dioxide. So this, I put this here for you to remember. That's where you put the coefficients, should you put them. So here's the molecular look at it. And this one, you're going to have carbons and oxygens on both sides. I suggest you write down when you are new to balancing equations, write a vertical line in the middle and write the number of each type of element one beside the other. So carbon on this side should coincide with carbon on the right side, side by side. Same with oxygen. And then you're going to figure out how many. You have one atom here or 1 mole, and you have 2 moles here. On the other side you have the same, so you are balanced. This one you don't have to do anything. So the mole ratio is 1:1:1. So let's look at this problem. Hydrogen gas and nitrogen gas produces ammonia gas. So this is definitely not balanced. And we have hydrogen and nitrogen, and 2 hydrogens here and 3 hydrogens on this side, and then 2 nitrogens and 1 nitrogen on this side. So you can balance anything when you begin, like anyone. So I'm just going to balance hydrogen here. So I need to make this side and this side equal to each other. Since 3 and 2, the smallest common multiple is 6, I'm going to make this side equal to 6. So 2 times 3 is 6. So I'm going to multiply this by 3. And then on this side, I'm going to multiply this by 2 to make it equal to 6. And I will put a 2 over here. Now, this one is, top one is balanced. And nitrogen, we got a 2 here. And so now nitrogen is balanced. Everything is balanced. So the mole ratio for this one is 3:1:2. And if you add the remaining molecules, it will look like this. And if you count the number of atoms, there are 6 brown atoms on both sides and 2 blue atoms on both sides. So there's a conservation of atoms and a conservation of mass. So when this product is formed, you will not see any hydrogen and nitrogen left. All you will see is ammonia. If you break down ammonia into its component parts, you will recapture the ingredients again, and there will be no products left. So problem 3. Here's a situation of polyatomic ions, and you are going to treat it as one thing, and we are going to look at metals displacing hydrogen. So you have to predict the products. So can hydrogen be kicked off by sodium? Yes, sodium is on top and hydrogen is at the bottom. So sodium will make sodium sulfate, that is going to be Na2S. And hydrogen gas. And then you're going to balance both sides. You have your hydrogen, you have your sulfate acting like one thing, and then you have your sodium. You have 2 hydrogens here and 2 hydrogens here, so hydrogen is balanced by the looks of it, and you have 1 sulfate on both sides, and you have 1 sodium on the left side and 2 sodiums on the right side. So you only have to balance sodium. So we are going to put a 2 over here, and then you multiply this by 2, and that is also balanced. And so the mole ratio here is 1:2:1:1. Problem 4. This is a metal reactivity series problem with 2 polyatomic cations, polyatomic compounds. These are 2 ionic compounds. And remember, you write the cation on the left and the anion on the right. Now these guys, when you have things like this, they can swap each other because one is always going to be more reactive than the other. So you have to predict the products. Aluminum will marry sulfate and make aluminum sulfate, and then magnesium will marry carbonate and make magnesium carbonate. You have to do the crisscross method to figure out their chemical formulas. And here we go, magnesium carbonate and aluminum sulfate. Now we have to balance the equation. So you're going to treat all the polyatomic ions as one thing. I've highlighted them for you. So here are all the ingredients. And remember, put magnesium side by side, aluminum and carbonate and sulfate side by side. So magnesium we have, let's start with sulfate. We have 1 here and 3 over here, so definitely needs to be balanced. Carbonate you have 3 here and 1 on this side. And aluminum you have 2 on the left and 2 on the right. It is balanced. Magnesium you have 1 on the left and 1 on the right. It looks balanced. So first what I am going to do is, you could either balance sulfate or carbonate, it doesn't matter. I am going to balance carbonate here by putting, since you have 3 carbonates, I'm going to put a 3 over here, and then magnesium changes. So I put a 3 over here, and then you're going to put a 3 over here as coefficient of 3, and that is going to multiply magnesium also by 3. And now we have 3 magnesium, so we have to make the magnesiums equal to 3 on this side. So I'm multiplying it by 3 and I put a coefficient here. Now we have multiplied sulfate by 3 as well. So I have to put a 3 on the sulfate on this side. So now everything is balanced on either side. So the mole ratio of this reaction is, I forgot to write it down, it's 1:3:1:3. And the next question, balancing, swapping cations and polyatomic ions acting as one thing. Can you predict the products here? So you don't have to worry about the metal reactivity series because ammonium is not a metal. You're going to make ammonium chloride and aluminum carbonate. You're going to swap partners. Here's your polyatomic ions, and here the other products. And then you're going to write the products and the reactants on both sides and balance them. We have 2 ammonium groups and 1 ammonium group here, and carbonate you have 1 on the left and 3 on the right, and then aluminum you have 1 here and 2 here, and then chlorine you have 3 here on the left and 1 on the right. So you can essentially balance with any of them. So I am going to start with this compound. So I want to make the carbonates equal to each other. Since we have 3 carbonates here, I want to have 3 carbonates on this side too. To do that, I need to multiply this whole compound by 3. And then what happens is you multiply this group by, you are going to have 6 ammonium ions. So I'm going to write 6 here, and you're going to have 3 carbonate ions. So carbonate is now balanced. Now your ammonium is not. So you have to go to the other side and balance ammonium by putting a 6 over here. And that will multiply ammonium by 6 and also multiply chloride by 6. So now ammonium is balanced and chlorine is not. So you have 6 chlorines here and 3 here. So the common multiple of these LCM is going to be 6. So you're going to multiply 3 by 2 and then you get 6. And aluminum gets multiplied by 2 also, and when you put a 2 here, and then they're both balanced. So the mole ratio here is 3:2:1:6, and you cannot divide this any further. Balancing equations problem number 6. Now we're doing combustion reactions. They are reactions in which compounds react with oxygen O2 gas and form oxides. We will learn about this in the last lesson some more. And these are a bit tricky, so you have to balance oxygen last. So let's look at all the ingredients, and the products all contain carbon, hydrogen and oxygen. You have 2 carbons on this side and 1 carbon on that side, 4 hydrogens on the left and 2 on the right, and then 2 oxygens here. And here's the key thing, I want you to write, don't combine all the oxygens here and write 3. I want you to write them, since there are 2 separate compounds with oxygen, you're going to write 2 plus 1. Whatever you do to this compound, you're going to change it over here. And whatever you do to this compound, you're going to change it over here. When you balance oxygen gas over here, you're going to add up the total oxygens here and make this side equal to that. That's our strategy. So first I'm going to put a 2 over here. You can start anywhere, that's where I decided to start. And when you put a 2 here, you multiply both carbon and oxygen by 2. So carbon becomes a 2 and oxygen becomes 2 times 2, which is 4. Now carbon is balanced. Now we have to balance the hydrogen. And you have 2 hydrogens here and 4 here. So we are going to multiply this hydrogen by 2 to get 4. And then they are both balanced. When you put a 2 here, you multiply this single oxygen by 2 also. So now the total oxygens you have is 2 times 2, which is 4, plus these 2 are going to be 6. So you have to equal this side to 6. So you are going to leave this oxygen alone until we've balanced everything. At this stage is when you change it. So the smallest common multiple between 2 and 6 is 6. So I'm going to make this side equal to 6 also. So I am going to do that by multiplying this one by 3. So I put a 3 here. And now I have the same number of oxygens on both sides, which is 6. And now my reaction is balanced, and its mole ratio is 1:3:2:2. Remember, when we don't write anything, it means 1. Last one, another oxide forming reaction. Here what you need to know is the carbon and hydrogen ratio is uneven. So sometimes you have to, this one is the most complicated, but it's very simple, as I will guide you through the steps. You have to multiply the first equation, the entire equation, by a whole number to get rid of a decimal coefficient. So we're going to start. Here's the carbons, hydrogens and oxygens, and we have 3 carbons and 1 carbon, 6 hydrogens and 2 excuse me. Okay, let's try problem 7. So again we have multiple oxygens, but this time we have uneven carbon to hydrogen ratio. This one is the most complicated problem you will, type of equation you will balance. Again, you're going to balance oxygen gas on this left side at the end. So we have carbon, hydrogen and oxygen, 3 carbons and 1 carbon, and then 6 hydrogens and 2 hydrogens on the right side, and then you're going to write your oxygen split into 2 on the right side, because you have 2 components with oxygen. You have 2 moles. We have 2 moles here and you have 1 mole here. Now you can start to balance it with any of the carbon or hydrogen anywhere you like, but I'm going to balance over here. I want to make this side hydrogen equal to that side. So I'm multiplying this side by 3. 3 times 2 is 6. And then when I put a 3 here, I multiplied this one by 3 also. So 1 times 3 is 3 oxygens. And then I'm going to now tackle carbon. So we have to put a 3 over here to make both sides equal. And when I put a 3 here, I multiplied oxygen by 3 times 2, which is 6. Now we have 6 plus 3, 9 oxygens. Now, here's the problem. So what you have to do is, you can't have 9 oxygens here. 9 times 2 is 18. And this side is equal to 9. So we're going to instead put 4.5, because 4.5 times 2 is 9. And then we will be equal to both sides. But you can't have a non-whole number coefficient. So we are going to multiply the whole equation by 2 to get rid of the 4.5 and have a whole number. So now oxygens are balanced, but you're not done yet. You're going to multiply the whole reaction by 2, and like this, just like a math problem. So we are going to get 2 of this compound, and 9 of these, and 6 of these, and 6 of these. And here is your final answer. And now our mole ratio is 2:9:6:6. And you cannot divide this any further. Now let's look at our review. So when balancing equations, you must obey the law of mass conservation that states atoms are not created or destroyed in chemical reactions occurring inside closed systems. And this is why we balanced equations. We only change the coefficients such that the number of atoms on each type of element is the same on both sides. When dealing with polyatomic ions that appear on both sides, treat the ion as one element. Balance oxygen atoms last. The balanced mole ratio of coefficients should be the simplest whole number ratio possible. And then finally, ionic compounds made with metal ions can only be displaced by a stronger metal based on the metal reactivity series. And please practice all these problems again and watch this video as many times as you need to go over each of the problems and make sure you have a good understanding. If you practice many times, you will get the hang of it. And we will be using balancing equations much more in the coming units. So you have to be a master of this. Thank you, and I will see you in the next lesson and do the exit ticket.